Hi, welcome back. In the previous video, we learned how to find the rank of an m by n matrix. The rank of an m by n matrix, remember, is the dimension of the row space or the dimension of the column space. Those two things turned out to be the same. Even though the row space was a subspace of Rn and the column space was a subspace of Rm, they both turned out to have the same dimension, and that was called the rank. In this video, we're going to learn about a third subspace associated with an m by n matrix and use a theorem. So let's give the definition and the theorem at the same time. So the subspace is called the null space. The null space of an m by n matrix A is defined to be the subspace of Rn consisting of all the solutions to the linear system of equations A times x equals the zero vector. So it's a homogeneous linear system, and we call that the null space, and the notation is n of A. So it consists of all x in Rn such that A times x is the zero vector. All right, so let's prove the theorem. Let's prove that this is actually a subspace of Rn. So we have to prove three things. We have to first prove that it's non-empty. So we have to exhibit just one solution to the homogeneous system. Well, we know one solution is the trivial solution. So the zero vector from Rn is in the null space of A, so it's non-empty. We also have to show that n of A is closed under addition and under scalar multiplication. Let's suppose that x and y are two vectors that are in the null space. So we know ax equals 0 and ay equals 0. And suppose c is any scalar. So if we add x plus y and multiply that new vector by a, well, the distributive property says it's a times x plus a times y. Well, that's just the zero vector plus the zero vector, which is the zero vector. So it's closed under addition. If we take a times the scalar multiple of something in the null space, that's just a scalar multiple of a times the vector, which is just a scalar multiple of the zero vector, which we know is the zero vector. The null space, the set of all solutions to the linear system ax equals 0, that is a subspace of Rn. All right, let's look at the matrix that we looked at in the previous video. So recall we had a 3 by 4 matrix A, and we found that the row space was a subspace of R4, and that had dimension 2, and the column space was a subspace of R3, and that also had dimension 2, so it had rank 2. The rank of A is 2. And now we want to find a basis for the null space of A. Well, remember, we're looking for the solutions to the homogeneous system Ax equals 0. And when we find the solutions to that system, we use the reduced row echelon form of A. And we already did Gauss-Jordan elimination on this matrix. In the previous video, we found that the reduced row echelon form of A was the matrix B with two non-zero rows. And so now we can use those two non-zero rows to write down two equations that give us the solutions to the homogeneous system. So the first equation is x1 minus 1 over 14 x3 plus 1 half x4 equals 0. The second equation is x2 minus 11 over 14 x3 plus 1 half x4 equals 0. And now looking at those two equations, we see that we have two free variables, x3 and x4, and we can replace those with parameters s and t and solve these two equations for x1 and x2. So x1 is 1 over 14s minus 1 half t. x2 is 11 over 14s plus 1 half, or minus 1 half t. And now we can write all the solutions to the homogeneous system are vectors x1, x2, x3, x4 that all have this form. The first component is 1 over 14s minus 1/2 t. The second component is 11 over 14s minus 1/2 t. The third component is s, and the fourth is t. Now, we can break this vector up using a linear combination of two vectors with coefficients s and t. So we can write it as s times the vector 1 over 14, 11 over 14, 1, 0, plus t times the vector negative 1/2, negative 1/2, 0, 1. Now, every solution to the homogeneous system of equations can be written as a linear combination of two specific vectors. I'll call these two vectors v1 and v2. So that means that we've found a basis for the null space. So let's summarize what we found. The basis for the null space of A is a set consisting of the two vectors 1 over 14, 11 over 14, 1, 0, and negative 1/2, negative 1/2, 0, 1. The dimension of the null space of A is called the nullity of the matrix A. So the nullity of A is the dimension of its null space, and we found two vectors in the basis for the null space, so that dimension is 2. So the nullity of this matrix is 2. Remember, we found the rank to be 2. We have a theorem that says if A is an m by n matrix, then n is just the rank of A plus the nullity of A. So our matrix A was a 3 by 4 matrix, so n was 4. It's 3 by 4, m was 3, but n was 4, and we found that the rank was 2, the nullity was 2, and this theorem tells us that 2 plus 2 better be equal to 4, and it is. All right, so we're going to be using this theorem and these three subspaces associated with a matrix in the work that we'll be doing for the rest of this semester. And I'll see you in another video.